Okay, let's start doing the homework together. So this homework has 9 problems and it's due next Tuesday. Great. So problem number 1, FCC reactors are among the largest processing units used in the petroleum industry. Figure 1 shows an example of a unit. The typical unit is 4 to 10 meters in diameter, 10 to 20 meters high, contains about 50 tons of porous catalyst. It's fed about 38,000 barrels of crude oil, and it cracks these long-chain hydrocarbons into shorter molecules. To get an idea of the rate of reaction in these large units, let's simplify and suppose that the feed consists of just C20 hydrocarbons, and this happens inside your FCC unit. And then you're told if 60% of the vaporized feed is cracked in the unit, what's the rate of reaction expressed both as minus R, moles reacted per kilogram catalyst per second, and R triple prime moles reacted per meter cubed catalyst per second. So I'm looking for these two parameters, right? First one, let me just get the right thing. Okay, so the first one is right here, which I'm looking for moles reacted per second multiplied by 1 over kilogram catalyst, and the second one is moles reacted per second multiplied by 1 over meter cubed catalyst. So this is similar to the example in the slides, if you remember, about the human. So we have two things, first, or basically three things: this parameter, and then the dN by dt, which is moles per second. So let's try to get the kilograms of catalyst. I think this is given directly. So you're told that contains about 50 tons of catalyst. So you're already given that your kilograms of catalyst is equal to 50 tons, which is 50,000 kilograms, right? And in order to get the meter cubed per catalyst, you're given the density, which is 800 kilograms per meter cubed, right? It's right here. So basically you're gonna have 50,000 kilograms divided by 800 kilograms per meter cubed, and this will give you the meter cubed of catalyst, which is 50,000 divided by 800, and this is 62.5 meter cubed. Okay, so now I have these two parameters. Now I need to get the dN by dt, right, which is mole reacted per second. So so I'm given some information about the feed. I'm told the feed is 6,000 meter cubed per day, right? 6,000 meter cubed per day. And I'm given a density for this feed. I'm told the feed is 900 kilograms per meter cubed. So multiplied by 900 kilograms per meter cubed. So I can get, multiplying these two, I can get the feed in kilograms, and then I need a molecular weight to convert from kilograms to moles, right? So let's have a look here. So I'm told it's C20 H42. So I have basically C is 12 multiplied by 20, H1 multiplied by 42. So the molecular weight of this guy is what? 240 plus 42, 282 grams per mole, right? So I'm gonna multiply this by the molecular weight, which is grams per mole, but the kilogram here is on top. So I'm gonna flip it, multiplied by 1 mole over 0.282 kilograms, right? So once I do this calculation, I should get a feed of about 6,000 multiplied by 900 divided by 0.282. You're gonna get a large number. Let me just, let's see. It's about 19.15 times 10 to the power 6 moles per day. I'm looking for moles per second, so let's convert this to second. So I'm gonna take this guy, multiply him by 1 day over 24 hours, 3,600 seconds. And this will give me about 221 moles per second, right? So this is the moles, the feed, right? The feed. We're looking for the moles reacted. You're given an extra piece of information here telling you that 60% of the feed is cracked. So only 60% of this reacts. So moles reacted is just 60% of 221. And this will be basically, I'm just multiplying by 60%. And this will give me 133 moles per second. Okay. So once I have this number, I can plug them here to get my R prime and R double prime. So my R prime in this case, oh, doesn't look good. Let's just right up here. My minus R prime in this case will be kilograms catalyst, so it will be 1 over 50,000 multiplied by 133 mole per second, and my R triple prime will be 1 over 62.5 multiplied by 133 moles per second, right? And again, this is in kilograms catalyst. This is a meter cubed catalyst. And then you can calculate these numbers, just plug them in your calculator, and you will get the answer to this problem. Good. So number one, straightforward. Number two, 150 Kelvin and nonane thermally cracks 20 times as rapidly as at 950. Find the activation energy of this decomposition. So this is a very common type of problem, and this is a problem in which we use this equation from your last slide, if you recall. Ln R2 over R1 is equal to ln K2 over K1. It's always good to remember this equation because this will show up a few times. E over R, 1 over T1 minus 1 over T2. And what information are you given? You're given T1 is 1150 Kelvin, and it's already given in Kelvin, which is good. And again, you cannot use Celsius, you have to use Kelvin or Rankine. It has to be absolute units. T2 is 950 Kelvin here. And then you're told that at 1150, R1 is 20 times as fast as R2. So in this case, R1, or you're using R2 over R1. So R2 over R1 is equal to 1 over 20. I'm going to take all of this information, just plug them in here. So if I plug all of this here, so I get ln of 1 over 20 is equal to E. And again, you're looking for E. So you're looking for the activation energy, E over 8.314. And this is in units of joule per mole per Kelvin, multiplied by 1 over T1, in this case, 1150 minus 1 over 950. And if you do this calculation, let's plug it in, and you're going to get an E of what? Let's see. Then 1 divided by 20 multiplied by 8.314 divided by so you should get an E of 136051, and the units here, because this is in 1 over Kelvin, so this 1 over Kelvin cancels with this 1 over Kelvin, so you will get joule per mole. If you want to represent this kilojoule per mole, just 136 kilojoule per mole. Okay, so this is your answer. This is number 2. Okay, number 3, a reaction has a stoichiometric equation of A plus B equal to 2R. What's the order of the reaction? You might be tempted to say that, this is first order reaction or second order reaction just by looking at these coefficients. However, you have to remember from your slide that the reaction order depends on your reaction rate, not on your stoichiometry. So if you recall from your slides, it's slide number 26, or slide number 23 in the PDF you have. If I have a reaction rate minus RA is equal to K, CA to the A, CB to the B, CC to the C, my order of reaction is just equal to A plus B plus C, right? However, I get this order from the reaction rate, not from the stoichiometry, right? Since I am not given a reaction rate here, and I don't know if it's an elementary or non-elementary reaction, then the answer to this problem is you cannot determine it without experiments to get the reaction rate expression, okay? So again, order of reaction, you need to get your reaction equation, your reaction rate. Stoichiometry is not sufficient to do so. Okay, moving on. Problem 4. Given the reaction of 2NO2 plus 0.5 O2 will give me N2O5, what's the relation between the rates of formation and disappearance of the three reaction components? Okay, so let's recall from your slides, it's slide number 18. If you have a reaction of A plus B going to R plus S, the relationship between them is minus RA over A is equal to minus RB over B is equal to R over R is equal to R S over S. So again, reactants, I have a minus sign, products, I have a plus sign, and I'm dividing all of them by the stoichiometric ratios. Similarly, if I have a reaction of 2NO2 plus 0.5 O2 goes to N2O5, my reaction rates will be minus R NO2 over 2 is equal to minus RO2 over 0.5 is equal to R N2O5 over 1. Okay, so this is the relationship between the rates of formation and disappearance of the three components. Again, straightforward. Just follow the basics and solve your problem. Okay. For an enzyme substrate reaction, the rate of disappearance of substrate is given by this. So what are the units of the two constants? Okay, so I have minus RA is equal to 1760. This is my first constant. A E note divided by 6 plus Ca mole per meter cubed second. So this is just an exercise in unit manipulation. And again, this Ca and this A are the same. It's just two different ways to write down your concentration. And your concentration will always be in moles per meter cubed, right? So this guy is in mole per meter cubed. This guy is in mole per meter cubed. This guy is in mole per meter cubed, right? So just looking at the denominator, then 6 has to also be in mole per meter cubed because you can't add numbers with different units. So the unit of this guy is mole per meter cubed. So now we have this, so the denominator, I have 1 mole per meter cubed, and here I have 2 moles per meter cubed. So this will cancel with one of them. So at the top here, I have mole per meter cubed multiplied by 1760 will give me mole per meter cubed second. So this means that 1760 is just 1/2, right? So once these two multiply, I get this unit. So the unit of this constant in this case is 1/2. Okay, so again, it's just an exercise in dealing with units. You're adding two things, they must have the same units. Multiplying, might not have the same units, but you should always end up with your overall expression should have the same units on both sides of your equality, of your equation. Good. Problem number 6. For a reaction with stoichiometry A plus 3B is equal to 2R plus S, and with a second order rate expression, K1A multiplied by B, what's the relationship between the reaction rates? And again, this is similar to what we said earlier. If I have an equation AA plus B going to R plus S minus RA over A is equal to minus RB over B is equal to R over R is equal to RS over S. And you see that, here you have basically the same letters. So I'm going to get minus RA over 1 is equal to minus RB over 3 is equal to R over 2 is equal to RS over 1. Right, so this is the relationship between the four components. Okay, not sure why I did. Sorry, it's scan right. RS over 1. Okay, this is the relationship between the four components. Good. Let's move on to the next one. So this is a bit of a text problem. Maximum allowable temperature for reactors 800 Kelvin. At present, our operating set point is 780 Kelvin, which gives you a 20 Kelvin margin of safety to account for fluctuating feed, etc. So now with a more sophisticated control system, we can raise our set point to 792 with the same margin of safety that we now have. By how much can the reaction rate, hence production rate, be raised by this change? The reaction taking place in the reactor has an activation energy of 175 kilojoule per mole. Okay, let's write out our givens. So I have a maximum allowable temperature 800, however, we're operating at 780. So our initial temperature of operation is 780 Kelvin. This gives you some buffer to reach the maximum operating temperature. So now you installed a new fancy system and you can now operate at 792 Kelvin. And you're also given that the activation energy is 175 kilojoules per mole, which is equal to 175,000 joules per mole. Okay, so how much can the reaction rate be raised? So you need to find the ratios, basically R2 over R1. Okay, sounds good. So let's just, this is a basic plugging in problem, right? So let's look at the equation we have. So in this case, the equation I have is, or the equation which represents this is ln R2 over R1 is equal to E over R multiplied by 1 over T1 minus 1 over T2, right? So I'm just going to plug in my expressions here. R2 over R1 is equal to 175,000 divided by 8.314. And again, be careful of the units, because if you're using 8.314, just be aware that this is joule per mole Kelvin. So if you're given your activation energy in kilojoules, you should always convert it to joules. So now this is joules per mole. So now this makes sense, right? Multiplied by 1 over T1, which is 1 over 780, minus 1 over T2, which is 1 over 792. Let's take this here. So if you do this, you're gonna get ln R2 over R1 is equal to, let's see, 175,000 divided by 8.314 multiplied by 1 divided by 780. So I'm gonna get, and this will give me about 0.4088. And basically, if you get R2 over R1 in this case, sorry, becomes, just take basically the exponential is 1.505. Okay, so your reaction rate and production rate increases by 1 point, or your reaction rate is 1.5 times higher than your previous reaction rate. Good, and then just this equation, you're going to see it a lot. Get comfortable using it, moving around the different parameters, interpreting some text problems to match it, how to use it, etc. Okay, moving on, problem 8. For a given reaction, on doubling the concentration of reactants, the rate of reaction triples. Okay, find the reaction order. Sounds like a tricky problem, right? So I have a reaction, whatever it is, on doubling the concentration of reactants. So let's say I have minus, where is it? Minus RA. If CA basically 2 is equal to 2 CA1, then that means that R2 is equal to 3 R1, right? So if I double the concentration of reactants, the rate of reaction triples, right? So minus RA, let's say it'll be just some expression multiplied by CA to a certain power, whatever n. So if I just write this, minus RA1 is equal to K CA1 to the n, and then minus RA2 is equal to K CA2 to the n. And now if I get the ratios, and if you remember, CA2 is 2 CA1, so this is equal to K into 2 CA1 to the power n right here. And if I divide these two expressions, so I get RA2 over RA1 is equal to K into 2 CA1 to the n divided by K CA1, right? So what am I looking for really? I'm looking for the reaction order. So I want to find this guy, n, right here. And I know this is equal to 3, right? So the algebraic problem then basically becomes, these cases cancel out. Sorry, this is to the n here. This cancels with this. So it becomes basically 2n is equal to 3. So in this case, n is just 2 n becomes what? 1.6, 1.58. The 2n equals to 3, sorry. So n is equal to 1.58. Okay, should be able to do this, right? Just many different ways. You can take a ln, move this guy here, move this guy here, whatever. But it's basically, if you take a ln, you're gonna get n ln 2 is equal to ln 3, right? And then n, you just calculate it, right? You're gonna get n to be this number. Okay, so let's go over this problem again. So you're given for a given reaction on doubling the concentration of reactants, the rate of reaction triples. Find the reaction order. Okay. And again, just one thing you need to keep an eye on: the reaction order will always be with respect to the component in which I'm writing my reaction rate as. So minus RA is equal to K CA to the N. This is my reaction rate. It could contain other junk like CB, whatever, however, they will cancel out when doing your math, because I'm only looking at the reaction order with respect to A. So if I write this down, I get minus RAK CA to the power N, 1. And then when I double the concentration, I get the second reaction rate RA2 K CA2, where CA2 is twice CA1, right? And then I just divide them. RA2 divided by RA1 is equal to K 2 CA1 divided by CA1 to the power N's, only 2's not cancelled out, and I get 2N equals to 3, N is equal to 1.5. Just think about it, try to do it. It's a very simple problem. If you're still struggling with this, come to office hours. We can talk longer.